with the next presenter, Jelle Ulan from TU Delft. Jelle's doing, yes, just go. Jelle's doing his PhD since about a year in the NEON project. That's a project that is funded by the Dutch Research Council, together with 32 other PhDers in the Netherlands, looking at the acceleration of the green energy transition. So there are 4 PhDs in total looking at that topic of airborne wind energy within this larger doctoral training network. Actually, we have quite a lot to share. Take it away.
Thanks. Thanks for the kind introduction. Yeah, so I kind of want to design better kites, and we need simulation tools to do so. So that's also what I'll be talking about today. And in part, my efforts are aimed at generating or developing a reference model, a bit similar to what Dylan is doing, which was mentioned quite often yesterday, and for the wind energy, wind turbine people here. Almost approaching like an initial version of OpenFast. That would be nice. So I'll first be talking about what is a kite and what kind of kite are we considering. How is the kite controlled, and how can we simulate it? What have I been doing? What has my colleague been doing? I'll also talk about that. And how can we improve that work? So talking about a kite system, we have a wing, a bridle line system, kite control unit, a tether, and a ground station. You're all familiar with that. And to me it was for a while unclear, do we call the wing the kite or the wing? So I decided, let's just make it clear for myself. I call this the kite, the wing, the bridle line system, and the kite control unit together. And the wing is very flexible, and therefore it's prone to fluid structure interaction or aerostructural coupled deformation. Furthermore, the wing acts as a morphing aerodynamic control surface, which means that you can, or you have to deform it to steer the kite. So it's also prone to actuation-induced deformation. So today I will be talking about the TU Delft V3 kite, which is a 25 square meter leading edge inflatable kite. And for those of you familiar with kite sports, this is also used very often. So in black you see the leading edge and the tubular frame. In front the leading edge, and in the chord-wise direction the struts. And in white is the canopy. And that has been used for the simulations. So talking about how the kite is controlled, there are 2 options basically. We have a depower tape and a steering tape. With the depower tape, we can change the pitch angle of the kite with respect to the wind. What does that do? That essentially changes the angle of attack and thereby changes the aerodynamic force that is produced. Because there is aerostructural coupled deformation, this will change the shape of the kite. Then there's also the steering tape that can introduce an asymmetry in the kite that will cause the kite to twist, then it will yaw, then it will roll. Actually, all will happen at the same time, and that leads to a turn. Alright. So we need to build an aerostructural coupled model to take into account the actuation-induced deformation and the aerostructural coupled deformation. And ideally, we'd like to simulate those both at the same time. So we need to include the steering and depower tapes. You can see the tapes here. And as some efforts have been done in the past to develop a very high fidelity fluid structure interaction model, or aerostructural coupled, I tried to do it differently, more on the low fidelity side. So we use a particle system model, which is comprised of, particles, and the particles are point masses. So all the mass is lumped at the particles, which you can see the red and the black dots. These are connected by massless spring damper hinges or systems, and that all works quite nicely. And then I also indicated some pulleys because they're quite important and they have a slightly different model. And essentially what you can do here is put some force on the kite, it will stretch upwards, and then the spring will pull it down, and then at some point it will reach a convergence, and you need some dampers to do that, so that's how it works. We will also need an aerodynamic model, of course. So we're using a vortex-step method developed by Uri, also present in the room, and it's a potential flow method that is essentially an addition or an involvement onto a lifting line theory. And in 2D, it uses computational fluid dynamics field lookup tables. And why is this relevant? Well, especially for a leading edge inflatable kite, after the leading edge tube, there's a large gap where a lot of vorticity happens. So if you're not considering vorticity in 2D, you're going to be far off. So both aero and structural model are coupled, loosely coupled in fact, and in a quasi-steady way formulated, which means that whatever temporal time step, we assume there is a convergence. Okay, so we have a kite model. It's great. We know we need to deal with actuation-induced, and we need to deal with aerostructural coupled deformation. And what can we do with this model? How can we help the kite design process? Well, then we need to look at how the kite's actually flying. Well, we know it's a pumping cycle operation. There's a real out phase in which energy is generated, and there's a real in phase in which energy is needed. And if we look at the real in phase, it's a particular flight phase, we can discretize that or make it a bit simpler by assuming that a quasi-steady flight phase or quasi-steady state assumption holds over the flight phase. We can reduce the flight phase to operating points. And if we zoom in into one of these operating points, the kite kind of looks like it's here. And we see a reference frame, we see a wind reference frame and a body reference frame. And we need to assume an idealized symmetric condition at this particular location. And that is very relevant because otherwise we cannot make a computation, we cannot do simulation. So what does this idealized symmetric condition entail? Well, essentially, you're assuming that over the ZW and XW axis, there's a symmetry plane span, and the symmetry plane crosses directly through the middle of the wing, and also aligns with the Z body and the X body axis. Okay, so we have an idealized symmetric condition. And why is that important? Well, if we're trying to resolve this problem in a simulation, we essentially need to solve the 6 degrees of freedom. So 3 translational and 3 rotational. And then we need to find convergence over each axis. And by assuming this idealized symmetric condition, we can reduce those 6 degrees of freedom to mere 1 rotational, namely the pitch, and 2 translational over the Z and X axis. Okay, so by assuming this condition, we can place the kite inside a so-called virtual wind tunnel. And this is just a more conceptual thing to make it easier to understand how the simulation works. And we attach the kite at the bridle point, at the ground, so we say that that's the origin. And we use a ball joint constraint there. So using this setup, we can make simulations for the operating points of the real in phase, which are useful to the kite designer, because then he knows how the kite's form and force will look like during the flight. So if we look at the results, we see that the white dots indicated results from a photogrammetry study. So I've analyzed footage of the kite flying through the air, and I've separated that video into multiple video stills, some of its powered state and some of its depowered state, and I've analyzed the width of both. Those are plotted on the left and the right. The left corresponds to its depowered state and the right corresponds to its powered state, and it flies its power state, of course, during real out, and its depowered during real in. And in right, we see the results of the model, the particle system model. And as we can see, the results align quite nicely. Both show a decrease in width when going from the powered to the depowered state. You can also look at the aerodynamic coefficients. And I just took the CO alpha plot here, where we see that there's a difference between the kite's powered state and the kite's depowered state, as one would expect. And it's also plotted next to CFD results to see if it's approximately in the same ballpark, and yes, it is. So that's nice. Bless you. And then I would like to get back to the pumping cycle again. So the simulations we did would correspond to the real in-flight phase, or essentially operating points there. But what we can also do is look at the real out-flight phase, which consists of straight parts going on a diagonal, though. But with some assumptions, we could say that for this straight part, also an idealized symmetric condition can hold, and that means that we can now predict or approximate how the kite's form and forces would look like during both real out and real in phase. And this gives the kite designer a lot more knowledge to make better kites. But ideally, we'd like to do more. We would also like to deal with the turns, and that is part of my future work. But I would like to share some thoughts I've developed together with Roland. So going back to the virtual wind tunnel. Supposedly, we start asymmetrically actuating the kite. Then what happens? The kite leaves its symmetry plane, it leaves the symmetrical condition, and starts rotating to the side. Well, because there's only a ball joint constraint at the bridle point, there's nothing to restrict the kite from moving away. So it will start a perpetual turning motion around the bridle point, and it will just start rotating and rotating and rotating. And the rotations aren't physical because it doesn't rotate with its actual radius, it's rotating around the bridle point. So both the simulations don't converge, and so what the simulations show is not physical. So how can we resolve this? Well, I said, why don't we just hold the kite at the leading edge in place, so when we asymmetrically deform it, it won't move out of the simulation boundary. Well, that's nice, gives you a result, but it's not physical. There's another way to do this, and that is by considering that this virtual wind tunnel box is actually flying over the kite's pumping cycle. So you're essentially taking the reference frame and moving it along with the trajectory, and then if you only look at the reference frame, the kite should remain in place. And to simulate that sort of moving of the reference frame, one needs to impose the inertial force field that the kite experiences during the turning motion upon this reference frame. And what then would happen, if you do it correctly, is that the kite will try to start moving to the side, but there's an inertial force holding it back, and the kite will remain in place. So hopefully, next time I will see all of you, maybe at AWEC next year, and show you the results of asymmetrically deforming kite, which remains in place. And with that, I would like to go to my conclusion slide. Presented the aerostructural coupled deformation model, and it just seems capable of predicting the width change and the aerodynamic forces. I think that by using an idealized circular turning motion, I can approximate the asymmetrical deformation of the kite while it remains in place inside of the virtual wind tunnel. And I've been contacted by some companies that are interested in the model, and so I will try and see if I can also apply it to other industries. So I took a picture here of Beyond the Sea, who's using a similar kite. And yeah, that was it. Thanks for your attention.
Thank you, Jelle. I'm amazed about the creativity to outsource your PhD challenge to the audience here. So please come back with feedback if you have ideas. It's a challenging problem. Are there any questions or remarks or feedback? The virtual wind tunnel.
Thank you. Nice presentation. Very interesting. One question about the coupling. How many iterations does it take to get the convergence between the fluid structure?
It really depends on the geometry and inflow conditions, and I don't have a number for you.
But it converges like in any case, or do you also have divergence?
I also have divergent problems, mainly with when the damping constant is not appropriate. There's also problems with stiffness that can be too high, and you run into your CFL criterion problems. So essentially, you take a stiffness that's too low, and you just assume that the elements are rubber, and then you slowly crank up the stiffness until you're okay with how far the line stretches. Then you're taking a lower than physical stiffness, but your solution is still physical.
So far you've only coupled them in so you didn't consider any time steps, right? It was just one steady state.
Yes, just one steady state. Yeah. So I take the kite at some position in its power state, I pull on the depower tape, or actually I extend, so the kite will pitch upwards and finds a new equilibrium, and I just solve that state.
Makes sense. Thanks.
Thank you. I guess you want to keep the motor separated from a dynamic simulator, no?
Yes.
But if you want to put them together, maybe you can add more state, no, for the masses and simulate everything together. And that would solve part of the problem. But if you want to keep it separated, it's more complex. If you want to keep it quasi steady.
Yeah. So one of the ideas is to do go for a dynamic model on a system level, and then assume that the quasi-steady holds within that model. So you stop the simulation, then you run the deformation model, and you say, it stays rigid for one time step, and then for that time step you use the bigger dynamic model. So I'm not sure if that's what you meant, but that is one of the ideas. Okay, I think it should work.
Nice. Thank you.
So basically the kite flies dynamically along the trajectory, but the deformation follows in a quasi-steady way. It's always a static deformation from per time step. It's an idea, but we're just at the start of it. Any other question? Otherwise, thanks, Jelle.